Ladies and gentlemen, we're going to be talking about resonance structures and exceptions to the octet rule today. This is section 8.6 in your textbook. So you are going to probably want to read section 8.6 and do the sample problems in section 8.6 as well as this video. So please make sure you do that. Okay, so let's give you a definition of what a resonance structure is, and it's when you have two or more Lewis structures that are equally good representation of a molecule. It can be even up to three, four in some cases. So we did talk about how to use formal charge before to predict which is the best indicator of a resonance structure. Well, these guys are going to have formal charges that are equal. So let's talk about these guys. A really good example of a resonance structure here is going to be ozone. Sorry about that. Zero period just started. It's going to be ozone, and ozone is a molecule which is O3. Now, ozone, if we were going to calculate the draw the Lewis dot structure for this guy, is going to have 18 valence electrons. And so when we draw this guy, we're going to have a single central oxygen with two additional oxygens on it. The way we draw it is we have single bonds to a double bond with 6 valence electrons around one of the oxygens. Central oxygen gets 2, and then we get just 4 valence electrons around the final oxygen over there to give us a resonance structure. Now, we have a mix of single and double bonds going on here in ozone. And what it turns out is that ozone can also be drawn with a double bond going in this direction. And let's put in those valence electrons going around the oxygen. Make sure we have an octet on everybody. So each of these is an equal and valid representation of the ozone molecule. And so we would call these resonance structures because we've moved the double bond from one place to another. And the way we show that these are resonance structures is we draw a little arrow pointing back and forth like this double-ended arrow, and that lets us know that these guys are resonance structures. Now, something that's very interesting that comes up in experimental observations is if they measure the bond length of the ozone molecule, it comes out to be about 1.278 angstroms for the single bond length, and when they measure the other bond length between the other oxygen, it comes up the same, which kind of goes against what we talked about before with respect to single bonds being longer than double bonds and triple bonds being the shortest. So there's got to be something else going on here, and the best way to describe it is these guys are what we call a blend of single and double bonds. And a very simplistic explanation of that is if we think of a bond as not a fixed line, you know, we've got them drawn as fixed single, double, or triple lines. They're not really. They are electrons being shared, and electrons are moving constantly and moving very rapidly, and they have that positive pull coming from the nucleus, the protons in the nucleus. So it is possible that these single and double bonds could be kind of oscillating, if you will, going back and forth, where one oxygen here has a single bond, and in the next moment it's the single bonds over here, and they just swap back and forth as these molecules are moving. We like to say that they're also a blend. Okay, so and that's going to come into play here in a little while when we talk about bond lengths and resonance structures. So let's kind of come down here. The next question is going to ask us, I'm just going to give you an example here, is to draw the 3 resonance structures of the nitrate ion. And nitrate, as we know, because we've memorized all our polyatomics, is NO3 1-. And so if we're going to do the number of valence electrons, 5 in nitrogen, we've got 3 times 6, and then we're going to add in that 1 extra electron there to give us 24 electrons to play with here. So I'm going to start drawing these nitrates down here. So we have a single nitrogen in the center, oxygen, oxygen, oxygen. We'll single bond everybody. That uses up 6, and we'll go 8, 10, 12, 14, 16, 18, 20, 22, and 24. And you'd think, hey, that's great, except if you look at that central nitrogen, the central nitrogen does not have an octet. So what we could do is say, hey, you know what, let's erase off a couple of these down here, and we'll make a double bond right here. And of course, because this is a polyatomic, we're going to put it in brackets, as we learned the other day, and a 1 minus charge on the outside. Now hopefully you're seeing that, hey, that's not the only way we could draw a nitrate, and it's not. We could draw it as a resonance structure, and I'm going to draw another one over here. Central nitrogen, oxygen, oxygen, oxygen. Well, that double bond could be going this way. Now I'm going to do something that I may have done before. I didn't really talk about it, but instead of making dots, I'm just going to make lines. Each line represents 2 valence electrons, which is a valid way of doing things here. You can do that way too if you like, or draw the dots if you want to as well. And we could also draw this nitrate with a double bond going in this direction. Put our valence electrons in here. Each line again representing 2 valence electrons, just like that. And so now we have the 3 resonance structures of the nitrate ion drawn. Okay, now here's a trick in the length of the bonds of the resonance structure, and this question has been asked on the AP exam. Remember we talked about how single bonds, that's a weird looking, hold on, let me rewrite that one. We talked about how single bonds are our longest, and we talked about how triple are our shortest bonds. It turns out that in resonance structures, we did talk about these guys as blends. A blend of bonds and a blend of, just like you could do a blend of colors. So really what would happen here, we could say that the bonds in nitrate, and it's being specific, the nitrogen-oxygen bonds, these guys are going to be shorter than a single, because remember single are the longest. Even though there is a couple single bonds in here, remember they kind of oscillate in between, but they're going to be longer than a double bond. So they're kind of in between a single and a double because you've got this resonance structure going on, if that makes sense. So that question has been asked on the AP test, so you should understand what's going on there, especially if you have resonance structures present. Let me scroll down here. We're going to talk about 3 exceptions to the octet rule. In regular chemistry, if you remember, we said you always have to make an octet, which meaning 8 valence electrons around an atom in bonding, or 2 for hydrogen. But here's the exceptions. As AP Chemistry, we're all about the exceptions. So let's talk about these ones. The first one is if we had an odd number of electrons, and this can happen sometimes. We sometimes do get an odd number of electrons in an atom, and a great example of this is going to be nitrogen monoxide, NO. Now nitrogen monoxide, if we're going to do the Lewis structure of this guy, we would have 5 valence electrons. We would add in 6 valence electrons, and we have a total of 11 valence electrons. We're going to single bond to start this guy out, just like this. Placing so that used up 2, we have 9 left, and so we have 7 left now, 5 left, 3 left, 1 left, and there's no way to get an octet here. So we're just going to put that last single bond on the nitrogen, and that's the best we can do. It's less than an octet, and it does happen sometimes. Okay, I'm sorry, we should go back. This was the odd number, and we did have less than an octet occurring on the nitrogen. Fewer than an octet will also occur, kind of a special case. It does happen occasionally with boron or beryllium. This is where we see it most often, and a really good example of this guy is going to be boron trifluoride. And what's going to happen here is we're going to have a central boron, 3 fluorines around it. If we're going to go through and calculate our valence electrons, we have 5 plus 21, which gives us 26. Single bond everybody, uses up 6. We have 20 left to deal with. 2, 4, 6, 8, 10, 12, 14, 16, 18. I got to double check my math here because I think maybe I'm off. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I did my math wrong. It should be just okay, of course, I just found I had to pause it there. Something just wasn't working out properly, and maybe you saw what wasn't working out properly. What I did was I used 5 for the number of valence electrons on the boron, in case it actually is it is 3. So I should be at 24, and then the math works out right. Now, we did just talk about resonance structures, and you might be looking at this guy going, hey, couldn't you just single bond one of the fluorines to get an octet on the boron in the central? And then we'll just make 3 resonance structures, and the answer is we could. But it turns out, because of the high electronegativity on the fluorine, because fluorine has such a high electronegativity, it doesn't form a double bond anywhere. It's going to really hold onto those electrons, so we get fewer than an octet. And like I said, this is typically with beryllium and boron, and it's typically on high electronegativity atoms where you're dealing with nitrogen or fluorine. Sometimes when you're dealing with central or some oxygens, not central, and some nitrogens, because those are our 3 highest electronegativity atoms. So we might see these occasionally going on. The last one we're going to talk about today is the more than an octet. These guys occur in period 3 or greater. And the idea is they're using empty d orbitals, which do appear in n equals 3. So more than octet can occur. Also, regular chem, we always said we're always trying to get an octet. Now we're saying, hey, sometimes we can get more than octet. So PCl5 is a great example of more than an octet that occurs. So we have a central phosphorus, chlorine, 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 and chlorine. We have 5 chlorines around this guy. If we were to go through and calculate our number of valence electrons, phosphorus is the one that does have 5. Chlorine is 5 to 7, 35. It gives us 40. And so we're going to go through and use up all our valence electrons. But if you notice in the center, and that comes out good, and if you notice in the center, that phosphorus has got, it's got 10 valence electrons bonded to it. 1, 2, 3, 4, 5 bonds coming off of it, which does exceed the octet. So that does happen, and it's okay. Phosphorus is in period 3 or greater, so it's using some hypothesized some empty d orbitals to take care of this. There is a rule of thumb that occurs. Just a general rule. If we have extra valence electrons, we're just going to place on the central atom. And that does happen occasionally. You'll get something like XEF4, which we'll talk more on Monday, which I will be back on Monday, about what goes on here and why a noble gas is bonding with somebody. But in this case, you will have extra valence electrons. You just put them on the Xe in the middle, and that's going to change the shape a little bit. We'll be talking about that in the next chapter. There's going to be some problems for you guys to do out of the white book or the blue book up on the board. Hope everybody has a fantastic weekend.